Okay, so just a reminder, the course website and everything, you can find the Moodle. Let me just pull it up and see if there's anything to highlight. Anyone know what the thing is on the screen, what it's called? What I just did? Say it louder. Okay, so two-factor authentication. We'll talk a bit about it today. What's the point of it? Security. Is it better than password? It's more secure? Yeah? Is there any disadvantages to it?
Yes.
Like? If you which? Okay.
The device for the two-pin verification is lost. Oh, you'll get stuck.
Okay. So you could lose your device. Does it take longer to log in? Frustrating experience? Okay. So just keep these things in mind. Okay. So the course website is on Moodle. Everyone should have access now. The lectures I took down last year's lectures from week by week, but they're still here. So all of the notes from last year are here, and all the videos are here as well. So they're week by week. But if you want to read ahead or anything like that, I actually think the course is better to not read ahead. But if you want to, they're still there. And yeah, so the videos I add, like usually tomorrow, like Thursdays, I'll add it sometime. I have to edit it like just slightly. And the notes and stuff I try and put up right away. Okay, before we start, assignment 1 I'll release maybe next week or the week after. So it will cover what we cover today in class is the nature of assignment 1. So I won't give it to you till after this class, but I'll try and have it posted by next week or the week after. Any questions about anything before we start? Okay, great. Okay, so where we left off, we're talking about evaluation frameworks. Just to remind ourselves, this is a high-level evaluation tool. So it's not going to tell you anything deep. And the expertise that you have, you bring with you in the experience of making this. So it's not going to let you become an expert in something that you're not an expert in. The deliverables, a very simple chart. So it's going to look something like this. And you're going to have different things that you might deploy. Usually they have some security consequence. You know, evaluation framework doesn't have to be a security thing, but for the purposes of this course, we'll consider it as a security thing. And then you're going to have some properties that it should achieve. Okay, so property 1, 2, 3. And then you're going to give it an evaluation or a score. And so to keep things simple, we usually just use either 2, like so it could be a dot or no dot. Sometimes you might think, oh, it's kind of a half dot. So the example I'll give today, we'll use half dots as well. But anyways, so it might look like something like this when you're done. And generally, if you do this and these are truly alternatives and there's no winner, probably it's not like one system has a whole bunch of dots and all the other ones have none. Okay, usually it's some sort of trade-off. So you could make an argument for using any of these. So like depending on what you prioritize. Actually, the way I drew it here, alternative 2 is you never use alternative 1 because alternative 2 is strictly better than it. But let's say we add a dot here or something like that, then there's not necessarily any reason to prefer one or the other. It's going to depend on how you rank each property, how important you think it is. Okay. Why isn't this working? Sorry, I was going to make that a half dot, so it was. Somehow this system, or the program's not working. I'll just restart it. All right, there we go. Okay, so the scale itself, I'll put it over here, is roughly like a kind of empty dot would be it does not achieve property or for fulfill. Full dot would be it does fulfill it or fulfills it fully. And then a half dot, you don't have to use half dots, but sometimes they're convenient. And then you could say it partially fulfills. Okay, so basically the method of doing this is you're going to start usually with your columns. So you'll define the columns, which are the evaluation criteria. So what does every column mean? Yeah, so it's an evaluation, but what I mean is when you write down a specific column, then you have to say what that means. Yeah. So what does it mean? So usually a couple sentences about what it means. And then you have to explain the scale. So what does it mean to get a full dot? Like not just in general, like, oh, it fulfills the property. Yeah, we know that. But like with that property, what does it mean to fulfill that property? Okay, so what does a full dot mean for that specific column? And then similarly, a part or none. Let me, I'll do it graphically so it's just a little cleaner. Okay, I mentioned this last time, but when you define the columns, you should define them positively. Which means that you play with the grammar so that you want, so it's phrased in such a way that you want the dot. So no dots are, like you wouldn't say, oh, this system is vulnerable to this attack. Because in that case, if you got the dot, then you are vulnerable and that's a bad thing, okay? So you would say this system is not vulnerable to this attack, okay? So you always want the dot. So a full dot is always the best grade. And then that just makes it easier to read. Then you can define your rows. Okay, and your rows will be alternatives for some purpose. Generally, it works best if they're true alternatives. So like choosing one means that you don't choose the other. Sometimes you can think about composition. So there might be, maybe you could do both 2 and 5 or something like that. So sometimes you can layer them on. So, and then you can try and show something about composition if you want using the chart itself. But anyways, for the purposes of this class, we'll consider things that are truly alternatives, meaning that if you choose one, you're not going to choose another. And then, yeah, we'll ignore like the idea of layering multiple of these alternatives on top of each other. Okay, so let's do an example. So we'll do it sort of interactively in class, and we'll do like a very light treatment of it. Then I'll show you an academic paper, and it's also linked on the Moodle. You can look through it. And they do the same thing that we do in class, but very much more formally, okay, and with like a lot bigger, a lot more rows, a lot more columns. So you'll see what it looks like to do it like kind of for real. And then in assignment 1, you'll be asked to do this yourself. And what I want from you is going to be like more detailed than what we do in class. What we do in class is just sort of interactive for fun. So it needs to be at a higher level of detail, more formality than what we do in class. It doesn't have to be like the full-fledged academic paper, okay? Some people want to do a project, so they like this idea so much that they're like, okay, let me do a bigger, better version for a project, and so that's fine. But in that case, you have to bring it like closer to the academic papers in terms of the amount of detail that you need to include. Okay, so what we're going to consider are passwords and alternatives to passwords. Okay, so we all know about passwords. It's something we use. Traditionally, the advice that you would get from a security person is have a different password for every website, right? So you might have accounts at 100 or 200 different websites. You should have a different password for each of them. You should memorize it. You shouldn't write it down anywhere. It needs to be long and complicated, not like a dictionary word or something like that. And so what we found is that that's not particularly usable. Okay, so people, you can tell them that as a security person, but people aren't going to do what you tell them to do. Okay, so they're going to reuse passwords across multiple sites, use passwords that aren't complicated, that are easy to remember, write their passwords down, any of the above. And so what people said is, oh, hey, like maybe there's a better way to do passwords. Okay, so instead of passwords, we could do something else. And the goal is usually always to increase security. Sometimes it's to at least not damage security, make it a more useful system without hurting security, or in some cases make security better. So those are the two sort of categories. So just to get us started, the one that we saw was, I'll call it 2FA for two-factor authentication. And the consensus was sort of like, okay, it's better. It somehow increases security. We didn't really drill down on why, but we'll circle back to that. But you know, you have to have your phone, and if you lose your phone, it's a hassle, and you have to always be typing it in and things like that. Okay, so maybe better on security, not as good on usability. Okay, so an evaluation framework is what we're going to use to sort of present that picture to someone who's interested in trying to decide between the two. Now, what are some other things? So you all use websites and web accounts, computer accounts. Besides just username, password, what are some of the other things that you've seen instead? So CAPTCHA, I think someone said. Okay, so a CAPTCHA is used mainly for recovering accounts. Or it's used to, sort of slow you down as you log in. So I won't include it, but CAPTCHAs are related to something I will include, which is...
to avoid the login of bots?
Yeah. Like when you drag the thing over?
Yeah.
Yeah, so all of these are graphical elements, okay? So the idea of, there is this idea of a graphical password. So a graphical password is actually a password. The most famous example would be Android. So to unlock it, there's a swipe pattern. So you make a pattern. And the idea is that it's more memorable than an actual password itself. So there's some usability studies that show, or they try and argue that. Some of them are recognition based. So they might say, here's 20 pictures. A bunch of them are picked at random. Some of them are like your password, like or whatever. When you set up your password, they show you 20 pictures and you click on one of them. and then they show you another 20 pictures and you click on one of them. And then remembering which pictures you clicked on, that would be your password. Or it could just be one picture and different points in the picture that you click on, that type of thing. So we can lump that together, and CAPTCHAs are kind of related to it, but they're sort of for a different purpose. A CAPTCHA, you always still have the username password. It's just something that's thrown on the end to like prevent spam bots and things like that. But we'll call this graphical passwords. Okay, what else? Just shout it out. Okay. All right, so fingerprints, facial recognition. So we'll call it biometrics as a kind of umbrella term. So for example, I'm an iPhone user. My previous iPhones had the fingerprint reader. New ones have a facial recognition. Doesn't work so much when you have a mask on because of COVID, but anyways. Actually, they did fix that, but then there was a reduction in the amount of entropy. So it's not as secure because it's only it's analyzing half of your face instead of your whole face. But okay, other things.
Questions? Recovering questions?
Okay. So we'll set recovery aside. So that's an example where it's not a true alternative. But it's a system that's closely tied to passwords. Yeah. So we'll put that in the same bin as CAPTCHAs. So let's call them password adjacent topics. So yeah, things like recovery, like what's your mother's maiden name, that kind of stuff. CAPTCHAs, you are related, but they're not actually true alternatives to a password. They don't replace a password.
Seared phases.
Say again.
Seared phases like in wallet.
Sorry, I didn't get it.
Seared phases that we have in the Web2 wallet.
Okay, sorry. Like you mean like a set of words that you would memorize? Okay, all right. So let's call this cryptographic keys. So cryptographic keys are like a password, but they're longer. That's basically the end of it. And normally you would store it as opposed to memorize. So a password is something normally you would memorize. In this case, you're going to store it. So you might have a hardware wallet, like a USB stick or something like that has your key on it. You might just store it on your hard drive or on your phone or something like that. And so that would be an example. Yeah. So encrypted drives, that type of thing. Sometimes they're still password based. Any Web3 crypto stuff uses them. SSH, if you SSH into a server, you have a private key and a certificate and that type of thing. So yeah. So a password manager. So this would be, let's have my browser or my operating system generate a password for me. And then it will remember it. And then generally I'll have like a master password, right, that unlocks it. So if someone sits out on my computer, they don't have access to all my passwords because they're all stored there. So you could consider it with or without, but for the purposes of the evaluation framework, let's consider it. I'll just put it in brackets with a master password. Okay, anyone work for government, military, anything like that? Or anyone know what they use?
The R is a device that they use for logging in. They're
Okay.
always changing the keys.
Exactly. So this is a kind of related to two-factor authentication. So it's a different form. Here for two-factor authentication, I'm going to do like what I showed you when I logged into Moodle. So we'll say it's SMS, an SMS code. But the alternative is what's called an RSA token. And so an RSA token is a little key fob. Now it could be an app on your phone, but anyways, let's consider the old school version. It's a little fob that's on your key. It has an LCD screen, and it could be LED too. And then it shows you a code. So you put your username in, you put your password in, and then you put an additional code as well. So it's something you know, password, and something you have, which is the token itself. Now, how does the server know that what you're typing in is right? If it's something that only you have and you have it on your keychain, then how does the server know, oh, that's the number that should be appearing on that person's key fob right now? Well, whatever, should it?
It was,
Yeah.
the buffer
Okay, just hold it for 1 sec.
about
Yeah. Okay, so it's not quite that. Anyways. Okay, yeah, so it uses some cryptography. It uses what's called a random number generator. It's deterministic. So the server has the same starting point and the device has the same starting point, and they spit out the same numbers in the same order on the same time scale. And then if you slip a bit, like if you enter a password that's 5 minutes old, the server will be, oh, maybe my clock's wrong, and then it will kind of synchronize. So that's okay. You had a question?
Yes. So isn't RSA token a form of two-factor authentication?
Yeah, exactly. Yeah. So these two are both two-factor. So to be more precise, what we could say is, we could just say like an SMS based. So basically we have two different ways of doing two-factor authentication. So let's put it this way. SMS 2FA. And then RSA, we can call it 2FA as well. Is that good? Okay. So the main difference here is one is your phone that you're carrying around, which you're probably carrying around with you anyways. The other is some special hardware device that you need to have. Okay. So the main difference between them, from a security perspective, they're almost equivalent. The main difference is, let's say you're offline, like, I don't know, you're out I guess you probably wouldn't be logging in, but maybe you're logging into a computer or something like that that's not online. You can't use SMS if you don't have cell phone service. If you're on a plane, for example, but you could use an RSA token. Maybe. I'd have to think through because it technically has to talk to the server. So maybe they both fail in an offline world. If you're a company, like say you're Concordia, right? So Concordia is deciding, should we, by the way, do you guys have to do two-factor yourself for Moodle? It's not just faculty, it's students as well? No? Okay, so anyways, as faculty, we have to do it. But anyways, you're at Concordia, you're the president, and you're saying, okay, should we do RSA or should we do two-factor? Well, most profs have a phone, right? And so if we do two-factor, it costs us, we have to change our server software or whatever, but there's no cost to us. If we do RSA tokens, then we have to give a faculty member an RSA token, right? Maybe they're only $5 or $10 or something like that, but you have thousands of faculty members, and then there's the whole logistics of handing them out and registering, it with the person and things like that. Like it's much more costly. So anyway, those are some of the differences. So we'll want to capture those in our evaluation framework.
So what government uses?
So almost all like Canadian federal government. I don't know, actually, they might have switched to two-factor authentication, but traditionally they used it like maybe as of 10 years ago. And in military, like Army, intelligence, security, advisory, those types of organizations use them as well.
Back around 2015 to 2018, I also used such kind of authentication.
Okay, nice, yeah. So now it's been like sort of, I think two-factor is sort of taken over just because it's easier to deploy, but yeah. Okay, so we have 1, 2, 3, 4, 5, 6, 7. Which one did I miss last year? Oh yeah, there's one other one. Let me think of an example. Yeah, I can't think of a great example that would lead you to the right answer, but like a lot of times if, let's say you download a new app on your phone, let's say it's a game, they want you to log in, right? Do you have to create a new username and password for that? So sometimes you do, sometimes you don't. If you don't, why? Like what would you do instead? Okay. So what you can do is, we call it single sign-on. And so this is the idea that you would, if you have a Facebook account or a Twitter account, you would just log in with your Facebook account. You're not logging into something that Facebook produced. It's some game. Facebook has nothing to do with the game. Okay, but Facebook offers this service that if you want to uniquely identify your users, instead of them having to create a new username password for your game, they can just sort of use Facebook's. Okay, so you log into Facebook if you're not logged in. You authorize it from Facebook saying, I authorize, and usually it shares a bit of information, and then you log in. Now, why does Facebook do this? This is maybe a good question to ask at this question. I mean, it costs them money, right? Every time like one of these things, like you're getting their servers getting hit with more traffic at a minimum. Plus, they have to maintain a database of all of these accounts and permissions and things like that, right? So, is it because the goodness of their heart that they want to help alleviate it? Okay. Okay. So every time I use this game, which isn't from Facebook, right? It has nothing to do with Facebook. Normally, Facebook would have no idea if I'm playing the game or not. If I use single sign-on and I link it to my Facebook account, every single time I play the game, Facebook knows about it. They know what game I'm playing. They know maybe how long I'm playing it, how often I play it during a day, right? So it's data for them, private data, okay? So that's why these companies do it. There's a lot of money in that data. So now Google has it, Facebook has it, Twitter has it, Apple has it, probably, I don't know if, yeah. And then you get targeted advertisements, cookies, and all that stuff that goes along with it, which we'll talk about. That will be a theme that comes back a couple times in this class. Okay, so we have 8 alternatives. Then what we want to do is we want to compare them. Okay, so we want to say, first off, is there a clear winner amongst these 8? Is there one that everyone does everyone use one of these now? Okay, most people use some alternative to password, but what I mean is, has the whole world switched to biometrics and you never see any of the others? Or is there any that's like that? No, it's still a big mess, right? Like Concordia is using 2-factor, Android's using graphical passwords, iPhone's using biometrics, crypto stuff's using keys. Apple has a password manager and they have a single sign-on, right? And so like no one's really committed to one of these solutions. And the reason is probably because there's no winner, okay? So they all have kind of trade-offs. They're all good for some things and bad in other regards. And so, and so that's what we're stuck with. And so it's been like this for 20 years, right? Like people have been trying to replace passwords. They've been talking about graphical passwords and single sign-on and all of these things. I would say in the last 5 years, we've seen some traction. Like almost no one does just a straight up username password anymore. Most people try and do at least one of these. And at least you have the option of a password manager if you actually prefer. I use a password manager myself. Apple's keychain one is great because it synchronizes across all my devices. Of course, you have to have all Apple devices, right, for that to work. But if your laptop's Apple, your phone's Apple, your TV is Apple, whatever, you can always have your passwords at your fingertips. And then it will generate like high entropy passwords and things like that. And then I use a unique password on every site. So in my world, I actually prefer a simple website that just asks for a username and password because I have a manager that can remember it, right? I don't like all of this other stuff because it's harder to use with my password manager. But for other people, right, they don't like password managers, they don't trust them, you don't trust Apple, whatever the case is, then you're going to want to look at some of these other solutions. Okay. So let's think about how, if none of these are winners, that means there's pros and cons to each of them, right? So what are the pros and cons of them? So what we'll do is we'll look at it in terms of security, since it's a security course. And then the trade-off with it are things that I've sort of mentioned in passing. Like I mentioned cost, right? That could be one of them. Going and changing servers, right? You have to open up a server, you have to put it up, it's going to accept traffic, it's going to manage some data, right? So all of that kind of stuff we're going to put under the umbrella of deployability. So deployability is sort of like how easy is this to deploy? So the easier it is to deploy, the more likely people are going to use it, right? So Facebook Connect, very easy to deploy. If you have a website, you just copy and paste code that Facebook gives you into your website and boom, it's done. Almost. I mean, there's a bit of a hook in order to pass the authentication back and forth. But, they make it as easy as possible, right? Deploying RSA tokens, then you're physically like giving them out to people and registering them and things like that. It's going to be low on deployability. Yep.
And the criteria should be the point of view of the user or the point of view of the, for example, Apple or Google.
Yeah. So we want to actually encompass both. So it's actually a good way. So let me put the third one we're going to call usability. Yeah, and so generally the deployability would be from the perspective of the service provider. And then usability would be from the user's perspective. Yeah.
Different tables.
So same table, different columns. Yeah, so this is user's view. And this is generally the service's view. And then security could be either. So some of the security property will be about the user, and some of them are going to be about protecting the service. So usability would be like, go memorize 200 passwords and make sure they're all different and high entropy. Obviously, that's a problem, right? You can't do that. So that's a usability problem. It affects the user. And if you give that advice, users cannot do it. They will not do it. And that's going to affect the security of your system. So there's a connection, even if it's a usability property. If it's bad on usability, people are either just not going to use it if they can avoid it. And if they're forced to use it, then they're going to use it wrong, right? And then that's going to impact security as well. So there's a direct relationship between these properties. And that's also what you're trying to showcase in an evaluation framework. So yeah, we call this a UDS framework. It's not the only way of doing it, but it's pretty useful. So UDS, usability, deployability, security, and it works for most things that you would want to analyze from a security perspective. You can argue that there's other kinds of columns that you should include. Okay, so for the example of passwords, or we'll call them password alternatives. So let's just brainstorm some first, and then I'll pick a couple out, and we'll talk in more depth about a few of them. So there's probably lots of things. Okay, so what are some usability criteria? So the example I gave, just to get us started. So the example I gave was memorizing a lot of passwords. Okay, so obviously a system would be more usable if you don't have to memorize any passwords. That would be the best case, right? Maybe if you have to memorize one password, like a master password, that's better than memorizing hundreds. And then you might have other systems where you have to memorize hundreds of passwords, okay? So what we want to do is we want to phrase that positively, okay? So we don't want to say, have to memorize 100 passwords and then give people dots or not dots on that, okay? Because we don't want people to memorize 100 passwords, okay? So we want to phrase it in the reverse way. So yeah, so the way we might do it is we might say nothing to memorize. That's the best case. Okay, what else? Just
Not complex to use.
okay. So we'll say we'll call it. Let's see. Okay, so let's split that up a bit. So I'll say low cognitive burden, which is like a very wordy way of saying it. But yeah, if it's like something like, take the name of the domain and reverse it and then add these digits on the end and that's going to be your password or something like you have to sit there, you have to think about it, or doing a CAPTCHA, even though that's not password related, that has a heavy cognitive burden, okay? So we don't want that. Now, why don't we want it? So first off, you have millions of users authenticating, so it's just a waste of everyone's time, okay? But in some cases, people can't do it, right? They might have a cognitive disability that prevents them from doing it, okay? And so accessibility is also another issue, okay? So for example, a graphical password, if you're visually impaired, can you do a graphical password? You can't, right? If you don't have motor skills, can you type in a password? maybe like you can, like there's accessibility technologies that let you do it, depending on what motor abilities you have, but it might be a lot more cumbersome and that type of thing, okay? So accessibility is something else that we want to look at. So we can say with users with disabilities, and then we might even split it up into different, like motor disabilities, visual disabilities, that type of thing.
Digital literacy. Having digital literacy.
Sorry, say it louder.
Having enough digital literacy.
Okay, yeah, that too, yeah. So that would be like kind of understandability as well. Yeah, so we could put that here as well. So, or we could put it here, like say understandable. The other thing with the cognitive burden is how efficient is it to use as well, right? So if we have two systems and they're equal in all regards, one of them you have to, I don't know, type something in and it takes 5 seconds, and another one you can just do it right away. You would prefer the one that you do it right away, okay? So efficient to use is also kind of related. So they're all sort of circling the same thing. Okay, let's say the system is, type in a password. Actually, let's go to dual factor authentication. Okay, so dual factor authentication, you type in your username, you type in your password, you get your SMS message, and there's a 20-digit number and you need to type that in. Is that a good system or not? Okay, so it's not very efficient, right? Because it's going to take you a while. What else could go wrong? All right, so let's say you make a mistake, right? Then you're going to have to start all over again, okay? So we would like...
When constraints come into action, then
Yep.
you get another one.
Yeah, exactly. Yeah. So let's say infrequent errors. We can think about recovery as well. So like, let's say you lose your phone, or you forget your password or something like that, then you have to go through the recovery process. You lose your finger, right? And you're doing biometrics, could happen. Okay, let's skip security for a second. We'll come back to that. What are some deployability things? Okay, so let's say, so once again, we want to phrase it positively. So if we say it costs a lot, then that's a bad thing. You don't want that. So we would say doesn't cost a lot or inexpensive.
Maintain.
Okay, meaning
Low maintenance.
for who, I should say? For the user or for the provider? For the provider itself. Okay, so maintenance is once it's installed. What about the act of actually installing it in the first place? So do you have to do anything to support it, right? So you're a website and you're choosing between all of these, right? What do you have to change about your website to make it a key as opposed to a password? Probably not much, right? If you want to do SMS, now you have to have a phone. You have to have a server that's capable of sending SMS messages. So you have to deploy that. If you're dealing with Facebook, you'd have to copy their code over, hook your thing up to Facebook. So we can think not just the maintenance costs, but the initial deployment costs as well. Yeah. So like how much do you have to change about it? Yeah. So let's I call it low complexity implementation last year. But yeah, all these the phrasing doesn't really matter that important. And then, yeah, we can add maintenance costs. So we'll say low maintenance. Actually, we might say the best would be no maintenance, right? Now, maybe no system gets a full dot on that, but you might as well be as strong as possible. So how many servers do you have to change? Do you have to change every user's device? Right, that's different than changing your website, right? Like imagine you have to install something on every user's computer, then you're making 100,000 changes. Whereas if you just change the server, it's all server supported, then you don't have to change anything. Okay. So let's say that you have one of these systems installed and you switch. You're going to have a bunch of users that don't have the new system. So what are you going to do in that case, right? So like, for example, let's say you switch to two-factor SMS. That's easy. Everyone has a username password. They still have a username password in the new system. They just have to add their phone number, right? So the next time they log in, you say, what's your phone number? Then they type it in, and then now they've switched, okay? They lose their phone, they report it. Somehow, credibly, you believe that they did lose their phone, then you just fall back on username password, right? That's good enough for now, at least. Get a new phone, tell us when you have a new phone number, right? Some of these, though, are a much bigger switch. Like switching to biometrics, for example, would be like completely different, or things like that, yeah. These ones are a little harder to come up with. Maturity is one thing that you might consider. So if the technology's been around, people have been using it for 20 years, that's great. If it's some new thing that someone proposed, some zero trust architecture or something that's like 2 years old, then maybe don't trust it as much. You can think of the computational complexity as well. So do you have to process this authentication? Like someone sends you, like say they send their picture, so the picture comes up and now you have to do facial recognition, you have to run some machine learning algorithm and classify it and things like that. And you have to do that every single time a user logs in, right? So that's going to add, someone has to pay the price for that computation, right? A password you type in, it's just like, does it match, yes or no? String matching algorithm, right? Very, very simple. So that could be an example.
Get benefit from user data.
What do you mean by user data? Like,
Track the user's activity and collect the data.
yeah. So that brings to mind two things. So one thing that we didn't talk about here is another alternative that's not here is called implicit authentication, which is sort of like you're looking at how the user behaves with the phone. Like sort of, are they using it? Are they, like there's keystroke patterns or like the way they're opening apps and the timing and things like that. And so that's called implicit authentication. So an example of implicit authentication actually is my watch. So my watch doesn't use it. It's sort of a hybrid system. So when I put my watch on in the morning, I type my passcode in. Okay, so it's just a password, okay? But as long as it maintains contact with skin, it will never ask me the password again, okay? As soon as it loses that contact, it says, oh, it must have switched people or something like that, then it's going to ask for the password again, okay? So that's a system where it's password-based to begin with, but then the session is basically, you keep re-authenticating through implicit authentication, which is that it looks like it hasn't come off my arm, yeah? So that would be an example of implicit authentication. Then with your phones and things like that, like if you log in, you type your password in, and then you keep using it, they're like, well, they haven't set the phone down somewhere. They're still using it. So you might like keep them logged in kind of thing. So that's also implicit. The other thing, so this is sort of a password adjacent thing as well. So it's something that you see when we're talking about passwords, but it's not really a true alternative. But let's say I don't know, I go to a conference. So there's a conference in a couple months in Croatia. So I fly there, I land there, and I open up my Gmail. And I logged in, I'm logged in. I have, keep me logged in Montreal. Gmail says, oh, actually, we want you to log in again, right? Why is that? Okay, so geolocation. So my IP address changed. It changed drastically. It went from one continent to another. And so it says, oh, I'm not so sure. Okay, so that's another way of using user data. So you might make different authentication decisions based on, like, oh, it's coming from a completely new IP address. Or I can see the user is logged in on one device from this IP address, and they're also simultaneously trying to log in from a completely different place in the world at the exact same time that I can see that they're using the first session, that their first session is active. So yeah, things like that are other things that you can kind of add on to these to add security. So I'll put it here. Okay, so let's think of security. So sometimes also you're like, where do these criteria come from, right? And so one way to invent them is just by looking at two of these things. So like, for example, if I say passwords, graphical passwords, like what's the difference? Why is one better than the other? Well, they're both passwords. They're both secrets. You both have to memorize them. The server has to remember what it was. You have to put it in. So like, they're almost identical, right? In fact, your graphical password could be converted into a string. Like if you do the swipe pattern on Android, that could be converted into a bunch of numbers. You could send the numbers and just call it a password, right? So the server doesn't even have to know that it's a graphical password as opposed to a password. But the big difference is on usability. So you might say, okay, well, what are some usability criteria that capture the difference? Well, it's better because maybe it's easier to memorize. So maybe it will have a property about memorization. But then if you're visually impaired, it's going to be worse. So maybe we'll have a property about that. So that's sort of how you come up with these properties as you think about what are the differences between them. So from a security perspective, what's the difference between, is SMS two-factor authentication better than passwords or worse? Okay, it's strictly better because it actually uses a password. Okay, so it can only be better because it can't possibly be worse, right? Because you still have your password there as well. Why is it better? What's better about it? So you check 2 times. Why is checking 2 better than, and why don't we check 100 times? Okay, so the trust model changes. Is it better or worse though?
Security point of view, yes.
Yeah, okay, but why? Like, yeah.
Because it's based on what you have and what you know.
Okay, so there's that aspect to it. So dual factor means, yeah, it's something you have and something that you know as well. Okay, so let's try and capture that in a security property.
It confirms data repeatedly.
Okay. Let me just put a pin in that one. Okay, why? Let's just keep drilling down. So something you know, something you have, that's fine. Why is it better to do both?
Something you know may be
From someone else.
Okay. So it's better because somebody might know what you know, but they might not have what you have. Okay. So if someone knows what you know, right, we could call that, so we could give it a name. So sometimes we call it impersonation attack. Okay. So having something you have in addition to something you know solves that impersonation attack. Okay. So that's the kind of, yeah. So sometimes you have to drill down on these properties and keep asking why, and then you arrive at a property. So we'll say like it's resilient to impersonation attacks. Okay, now let's keep drilling down though. Impersonation means what? If I'm impersonating you and it's a password-based system, what does that mean? So it could mean that I recovered your password accounts because I know your mother's maiden name. That's the most common example, okay? But set aside recovery. Okay, recovery is a different thing. We could do an evaluation framework of recovery. But just in terms of logging in, not using the recovery mechanism, if I'm impersonating, what do I know about you? If I can log in with your password, I know your password, okay? All right, so how did I come to know your password? Sorry, say it louder. Okay, so stolen credentials, or guessing the credentials. So both of those are valid. So it could be that okay, so I know something about you, so I know your interests, so maybe I guess your password. So that's more what we could call impersonation. It could be that I steal your credentials.
maybe
Okay.
social engineering. You call and reset the password. And
Yeah. So absolutely for recovery and resetting, that's true. Yeah. So that would fall under there. Now, if I steal your credentials, where am I stealing them from? Okay. So there's the application. So it could be like a password breach, password dump. So that's one way. How else can I steal them? Okay, exhaustive search. Okay, that's good. So we'll roll with all these. Anything else?
the dictionary.
So dictionary is exhaustive search. Eavesdropping. Okay, so where do I eavesdrop? Okay, so I can eavesdrop on the network connection. Let's say I do that. What am I likely to see? Anyone know the answer? Probably a bunch of encrypted traffic. Okay, so generally passwords are transported encrypted. Okay, so encryption is a tunnel. A tunnel has a start point and an end point. Where the tunnel ends somewhere at Facebook, Google, whatever I'm logging into. Where does it start? It starts in my computer. Like where kind of in my computer? Browser. Okay, so it could be the operating system or the browser. Let's say it's the browser. Okay. Is there any place, does my password have to travel through anything before it hits my browser? Keyboard. Okay. What if I go to Concordia's library, I take a little USB device, I unplug the keyboard, I plug it into the USB device, and I plug the USB device into the computer, and it records every key that's pressed. Okay? Then I go through the logs, 6 months later. Maybe it emails, it has a Wi-Fi or whatever, it just dumps it somewhere. And then I go through, and I'm like, oh, that's a net name. I recognize that. They type blah, blah, blah at concordia.ca, and then what are those next 8 characters after it? Right, or 10 characters, right? Probably their password. So this happened. It actually happened at Concordia's library, right? People were doing it for, no one knows how long they did it, but at some point the librarians went around and they discovered that there were a bunch of these things plugged into the keyboards. So resilient to, we'll call it, just to be like kind of fancier, we'll call it internal observation. So internal means like inside your computer. So it could be malware. It could be a keystroke log. Keystroke loggers are arguably malware, but it could be like a hardware thing, anything like that. And then what if I told you, oh, the keyboard's fine. The whole path from the keyboard to the browser to the SSL encrypted tunnel to the server, that's all fine. Okay? Is there any other way you could observe the password?
At the service providers and
Okay, so we're assuming that's all secure, all the way from the keyboard to the server's end. So between the user and the keyboard, what happens? Okay, physically, yeah. So I have to type my password in, right? So if someone's standing over my shoulder, watching me type it in. If someone has Google Glasses and they're watching me, they have a recording of it. If there's a security camera somewhere, they have it. Shoulder surfing is sort of informally, but we'll call it resilient to external observation. So shoulder surfing would be an example. Okay, and then back to dictionary attacks. So we talked about dictionary attacks. So resilient to guessing. And so back to this, like, why is two-factor better? It's something you have as opposed to just something you know and you have. So that's better. But it also gives you a big, long digit, right? And so even if the password itself is kind of weak, it's a dictionary word or something like that, then at least that big, long digit is random. It was chosen by a server, but it's random. And if the user is truly the only one that has the phone, has access to it, and knows that number, then that also helps secure the account. Because an adversary might be able to guess my password, but they're not going to be able to guess that code because there's too much entropy there. The Facebook example is a privacy property, but we could put it under here. This also, someone else said trust, I think. So like no trusted third party. So that also, yeah, it could have privacy implications, like you're funneling all your authentication through Facebook or something like that. We can think about theft. So by this I mean like physical theft, and specifically I'm thinking like stealing your RSA token, or stealing your phone in a two-factor authentication scenario, or stealing your finger, or at least your fingerprint for biometrics, that type of thing. So resilient to theft. Phishing could be its own thing too. Lots of people mentioned it. So you'll see that surprisingly some of these actually, you might not think at first pass that they do something about phishing, but they actually do something about phishing indirectly. Yeah, so, okay, so I won't talk about phishing. I won't do one of the detailed ones, so I'll go through this. So cross-site scripting, all that kind of stuff, we'll put that kind of under an internal observation. So that's sort of like malware, keystroke loggers, all that type of stuff. Phishing is basically someone sends you to a fake Concordia website. It looks exactly like the real one, and they capture your password that way. Okay, so that's fine. Do any of these help you with phishing? Okay, so password manager. So you might not think, what does a password manager have to do with phishing? Is it warning me about, no, it's very simple. You have your password for concordia.ca, you saved it, you don't even know it yourself. You go to a fake Concordia CA and you're like, oh, this is the real one. You go to log in and your password manager is like, I don't know what site this is. I've never seen it before, right? And if you actually truly didn't memorize your password because you had it generate it for you, then you can't even be like, oh, it's broken, so let me just type it in, okay? Now, you could do a lot of work like going into the password manager and like digging out the password and copy and pasting it or something like that. But hopefully all of that work is enough of a deterrent that you slow down and think, oh, wait, maybe this isn't the right website, right, that I'm logging into. So that's an example where, yeah, it actually helps with phishing even though you might not think about it. Okay, so let's pick a couple of these and we'll do the next step. Remember the steps are, in this case, we started with the rows, but anyways, we came up with a bunch of rows. We've come up with the columns. We have a sense of what they mean, at least informally. In a report, like assignment, you need to write down a sentence for all of these. Yeah.
So we spoke about shoulder surfing in the security conference.
Yeah.
Then I was thinking of a system which is secure to shoulder surfing because I feel like it's more on the user to prevent shoulder surfing than the system. So I have to prevent myself from somebody seeing the password. The
Yep.
system cannot do it for me. So how can you include shoulder surfing? Is it more on the social engineering side? How can a system prevent it?
Yeah, so if we go through these, we could say, okay, you can shoulder surf a password. I can shoulder surf your SMS message and your password. I can shoulder surf your graphical password, okay? Biometrics, can I shoulder surf that? No, so that's an example, for example. That one's like, you could argue, like, if it's your face, I could kind of like, I could hold your phone up to your face or hold my phone up to your face and mirror it to your phone or something. So like that one, like maybe that sounds like a half dot, right? But then cryptographic keys, let's say it's stored. The user doesn't do anything, right? The key, it comes out of memory, the operating system puts it there. So that's an example that's truly resistant to shoulder surfing. Yeah, because there's no input from the user itself. Yeah, so for all of these, and then let's say that you asked me the question, so I answered it for you, okay? But let's say you're at home doing this for yourself. At worst, what you would do is you'd have an empty dot all the way down, right? So you'd be like, oh, I thought this was a good criteria, but now that I fill it in, I see that like nobody has it. Then you might say, well, is this really a good criteria, right? And so you can learn something by having bad criteria, like everyone gets a full dot or nobody gets a dot. That can tell you something as well. Like, why did I think that you could achieve what I thought you could, or why some systems wouldn't. So it's actually useful to do that exercise anyways. Okay, so we have our rows, we have our columns, we don't have a sort of dot by dot, what do they mean? And then we have to do the chart itself. Okay, so let's keep going. So what I'll do is I'll pick a couple of these ones. I'll just pick the same ones that I did from last year. And then I'll show you a paper that has like lots and lots of different ones, even more than we came up with. Okay, so let's pick a usability property. We'll call it physically effortless. So I'm going to call it U1 for usability, because when we do the chart, I won't write all the words out. Okay, so we could do a half dot, sorry, no dot, half dot, full dot. Okay, so physical effort would be like, I don't know, typing a password in. That's a good example, okay? So do you even have to type a password in? So for biometrics, you have to type a password in? No. For a client certificate, you don't have to type them in. For two-factor, you have to type in something, your password plus something else, right? So two-factor would definitely be like a kind of full dot. Certificates would be like a no dot. So there's different ways of doing it, but we could say type, or because we have graphical, we could say /draw. So type draw every login. To get a full dot, you never have to type or draw anything. And then the middle ground, so once again, there's no right or wrong way of doing this. So you're trying to tell a story to the reader, and if we all did this exercise, we would come up with slightly different dots and things like that. So I'm not trying to say that this is locked in. So you might focus on how much you have to type in. So it might be like, oh, it's a short thing like a password, or it's a long thing like a password in an SMS code. You might focus on how many times. So if you log in 100 times, you have to type it in 100 times. If you log in 100 times, you have to type it in 0 times. Maybe there's some middle ground, like single sign-on, for example. Well, I have to log into Facebook, so I have to type my password in once. But once I'm into single sign-on, then I don't have to type it in the other 99 times. Or my password manager, I have to type it in once to unlock the password manager, but then I never have to type it in again. So that, for example, could be the half dot. So the half dot could be like type draw once for multiple logins. Okay, so it's sort of up to you to sort of shape the story that you want to tell, and there should be some meaningful separation. So you could think of on only this point, certificates, that kind of thing, biometrics are the best, right? And yeah, something where you just type it in once, that's definitely better than typing it in 100 times and typing it in 100 times. So it sort of works, it feels good, so then you kind of lock it in, okay? But there's an art to this as much as a science, and all of you will come up with different, even if I said do an evaluation framework on the exact same thing, you'll all have like slightly different columns, or even if you have the same column, you'll define what a dot means slightly differently, and that's okay. That's acceptable. Okay, nothing to memorize is another one that's important with passwords. So we can sort of follow the same criteria. We already have it. So it could be, there's truly nothing to memorize. You have to memorize 100 things for 100 logins, or you have to memorize one thing would be the sort of middle ground. So 0 passwords, just one, like a master password or a single sign-on, you log into that, and then everything else you don't have to log into. And then this would be like, you could say 2+, or the idea would be if you have n sites, you would log in n times. You have to memorize n passwords. Next one I just chose is nothing to carry. So are you carrying around something? So like an RSA token would fail on this. So it's something new that you have to carry. Here's this RSA token. You've got to bring it everywhere. If you ever forget it, you can't log in. It could be like, oh, we're doing two-factor with your phone, but you're probably carrying your phone around anyways. So yeah, you are carrying something, but it's something you probably have with you. Or you're carrying your cryptographic key around. Well, it's stored on your computer. You're probably carrying your computer anyways. Or you're logging in anyways from your computer, so you have your computer there. So we'll say there is something to carry, but it's common. And then it could be nothing to carry. And you can get like nitpicky, like is a fingerprint, I mean, you have to carry your finger around. It's something common, so you're always carrying your finger around, but it's not quite like your phone, right? Like you might not carry your phone, but you're basically going to bring your fingerprint everywhere, okay? So I would say that that's nothing to carry. So yeah, anyways, you can use common sense. It doesn't have to be like narrowed down to a specific science. Okay, we'll do a couple security properties. Okay, so the flagship property, security property of a password is it's long and it's hard to guess. Okay, you can't throw a computer algorithm at it or a dictionary and find the words. Okay, there's a lot more that go into the security of passwords, but that's like the main property itself. Okay, what does it mean to be hard to guess? So if I say I have a password and you want to, or yeah, let's say you get hired at an organization and you're supposed to go around making sure people are using good passwords or not. What's a good password? Okay, so how would you define difficult to guess though?
It takes years.
Okay, so it takes years. Okay, so it takes years to try every password before you hit the one that you guess. What about a password would make it take years as opposed to hours or days?
High entropy.
Okay, so high entropy. So what does that mean? That's the correct answer, but that sounds like a lot of math, like physics or something.
The number of characters, the combination of characters like alphanumeric, special characters.
Okay. So just let's go to the real basics. Is a longer password better than a shorter password? Okay, so generally, some people are saying not necessarily. Why? Is a long dictionary word better than, say, a short, like random password? Okay, so first off, let's say that random passwords are better than like user-chosen passwords. Like I'm going to pick a dictionary name, or even if I'm going to take my favorite song lyric and I'm going to take the first letter of every word, and it's going to kind of look like mumble jumble, but there is some structure there, right? So you have structured passwords that come from natural language, and then you have like truly random things. Random's always better, okay? So that's the first thing. So random's better. The second thing is that once we say that they're random, a longer password is better than a shorter password. A longer random password is better than a shorter random password, okay? And then we can also say that let's say that your password is only digits. So you have a 10-digit password, or your password is randomly chosen, but it's small characters, capital characters, digits, a couple special symbols. Which one's better? Okay, so the second one's better because there's more combinations, basically, okay? So it all comes down to like how many combinations of the password do I have to try in order to guess your password, okay? So normally I would start with some sort of natural language, like a dictionary or something like that, and that's how I'm going to hit your password. And then if I can't do that, then I could do true brute force. Is it 0000? Is it 001? Is it 002, right? Or AAA, AAB, ABC. And then, yeah, use exhaustive search, okay? So now, does anyone have a sense of how many characters are kind of like ballpark, like good? Like is a 4-digit PIN good? Is that sufficient or not? Okay, so how many combinations are there? 4-digit PIN? So 10,000, right? So from 0000 to 9999. Okay, so how fast would it take a computer to do 10,000? Like milliseconds, probably. Okay, so it's not secure enough. Now, why does your banking card have it? Your banking card has 4 digits.
But because after 3 attempts, it will block or something like that.
Okay. So what we have is we have a situation where passwords could be human chosen, that's bad. They could be randomly chosen. The longer they are, the better. Okay, so that's all on the user side. So that has to do with how the user chooses their password. Then on the system side, we also have countermeasures, right? Like your banking card, you put the PIN in wrong 3 times, it's locked. Then you still have to authenticate some other way, right? You have to go to the bank in person, show your driver's license or whatever. So a 4-digit PIN actually isn't that bad in that scenario, right? If I go to Facebook and I'm trying to log in and I put in AAB, I write a script to do this, AAC, what's Facebook going to do? Are they going to sit back and let me hammer a million guesses at your password a second? No, they're going to lock me out. They're going to be like, okay, that looks like someone exhaustively searching, okay? So it's also going to make a difference of what kind of access do I have to the password to guess it, okay? Do I have to go through a web interface to guess it? Do I have to go through an ATM to guess it? Okay, in that case, I don't need as much entropy. If I, on the other hand, let's say I have a hash of your password, which is kind of like an encryption of your password. It's sitting on my computer. And if I put the right code in, it's going to like unlock that hash, or it's going to hash to the same value. In that case, I can do it as fast as I can. Okay, I can get cloud computers, botnets, whatever. You know, that's just, it's all on me. It's just a limitation of how fast I am. I have your encrypted password. I have my guesses at what it is. And the faster I can guess, the faster, you know, I break your password. Okay, so sometimes we distinguish between an online attack and an offline attack. So an online attack would be, you have to go through an ATM. I have to go through a website. The website's going to rate limit me. And in that case, I can get away with a 4-digit PIN. Okay, but if it's a hash of a 4-digit PIN, I mean, it doesn't stand a chance. It's going to be cracked in milliseconds. Okay, so our resilience to guessing depends whether we're in the online model or the offline model. So to kind of put some numbers on it, a good number, I kind of made this up, but there is some backing of it, would be something like 2 to the power of 40. So that's a pretty big number. That means you double something 40 times. And it doesn't sound like a big number, but it's like bigger than the number of grains of sand on the earth, or I don't know what all the analogies are, the number of stars in the universe, that type of thing. Like it's actually a very large number. When you take a crypto course, you'll appreciate how big that number is. But 2 to the 40 is definitely, you can brute force that with a computer, okay? Might take a bit of time. It might be more in like the hour range for a laptop or something like that, but I can do it with my laptop. I don't need a supercomputer, okay? So if it's going to be something less than this, in fact, actually, let's make this a little bigger. Let's go to, let's do 2 to the 64. Okay, so most user chosen passwords would fall somewhere in here. A strong cryptographic key is going to, NIST says, so NIST is the regulatory body, you know, for crypto, at least in the US, and Canada follows their recommendations. They say your keys have to have 112 bits of entropy. In other words, you have to have 2 to the 112 possible combinations to that key. And you can't exhaust that by today's standards. And we also think it will be secure for the next 10 or 20 years. Okay, so this is like kind of cryptographic level. And in here, you could have something that's sort of like a machine chosen password. So like a password manager would drop you into this sort of category. Like they're probably not quite at the cryptographic level, but they're close. Or let's say you do a 2-factor authentication. By the time you get your password, I have to guess it, and I have to guess the phone code. The phone code adds a lot of bits onto the end, even if it's like a 6-digit number or something like that. It could be enough to put it into this category. I guess so at Concordia they use I think an 8-digit number, so that would be 10 to the power of 8. So that would be about 2 to the 3 times 8. So it would be about 2 to the 24. So that's still actually, like, that would still fall. So the SMS would still fall into this kind of range. But anyways, guessing it's not a binary like this is enough, this isn't enough. It's kind of a spectrum. And then you have the complexity of whether you're sort of offline or online. Okay, so to sort of break this up, what we can do is we can say, just as a kind of rough pass, we can say, okay, S1 is going to be resilient to online guessing. And S2 we can say is resilient to offline guessing. So this is the stronger property that would be harder to achieve. And so for this, let's just keep it simple. We'll do a no dot and a full dot. Okay, so we'll use 64 bits as kind of the cutoff, or 2 to the 64. So less than 2 to the 64 or greater than 2 to the 64. And we'll use less than 2 to the 112 for this and greater than 2 to the 112. Okay, so user chosen passwords, they kind of fall in here. Machine chosen passwords would fall into here. SMS we'll maybe put here. Maybe 64 is not exactly the right number. Things like biometrics would also fall into here. So biometrics are like okay, but they're not the best. They're not the highest category of entropy. They're sort of in the middle. So you can't, I'm just telling you what I know. So like if you were doing this for yourself, you would have to like look at some papers and try and figure out, like say, it's Googleable. You could be like, okay, how much entropy is in a fingerprint? And then there'll be a bunch of papers and they'll say, well, we looked at 1 million fingerprints and we estimate that it's about 34 bits or whatever. Yeah. And then you can include more information or less detailed information, but then it's more likely that you have a false positive or a false negative, like it's truly your fingerprint and you're not logging in because your sensitivity is higher. So then there's also that parameter that you have to switch on and off. And so finding the right balance is kind of hard. But in this case, we just want kind of broad strokes. So in broad strokes, what I would say is if I have a hash of your passwords, like your fingerprint sitting on my computer, I can probably exhaustively search it. But if it's like a banking system or a phone, and if I put in 10 fingerprints, it's going to lock me out, then I'm not going to guess it. I'm not going to guess it in the first 10, right? But if I can throw a supercomputer at it, I'll probably guess it. So in that case, what we'd say it's resilient to online guessing, but it's not resilient to offline guessing. Does that make sense? Okay. All right, so let's take a break for 10 minutes. So it's 5 after 4, so we'll come back at around 4:15. And yep. Okay, what I'll do is, the last point was maybe not the clearest, so let me, this I think will be good background information. Let's just go through the life cycle of kind of like a password and how it works, just so that you can, I'll try and write down basically things that I said, but I think they're important. So we start with a user, okay, and they're going to, so to get a password, you have to register first, okay? So the first flow will be registration, and then the second flow will be you're coming back a second time, you're going to put in your username password, and then the server is going to decide whether you're the same person or not, okay? So first off, you have to like type, we'll consider this for like normal passwords, and then obviously the flow is going to change a bit for the other configurations, and you can think that through. I won't draw them all out, but okay. So you have a user, they have to like physically type their password in, okay? So that can be the first step. So here's their like computer. And so they're gonna like type it in. And so things that could go wrong is you could have an adversary here looking, shoulder surfing. You could type it into the wrong website, so that would be phishing. So those are the kinds of attacks that you might see here. Then in the computer itself, you have like the keyboard, and so it's sort of going to go from, you know, I don't know, keyboard. Then it's going to go through the driver for the keyboard. And then the operating system manages the driver. And then the operating system is going to say, okay, there's this new key event someone's typing, and I'm going to pass it to the browser. And then the browser will dump it into the form post or whatever, the HTML that will capture it. And usually you denote it's a password, so we'll put the asterisks in, and that's like the HTML of the website that's being implemented by the browser. So all these details don't matter, but the point is that this is kind of like what we would call internal observation. So if you have a keystroke logger, it could be, you could have a logger on the keyboard. You could have malware anywhere really in here. Some sort of cross-site scripting, web vulnerability that would come into play, like in the browser itself, like the website, or somehow you have a resource that's loaded on the same page, and you're able to pull that form element out. That type of thing would happen here. So it doesn't matter if you don't understand what this is. We'll actually circle back to this at the very end of the course. But the point is that all of this stuff is kind of like internal observation. We could call this external. So this could be like shoulder surfing, that kind of thing. Okay, so once it ends up in the browser, then what your browser will do is it will create an encrypted tunnel to the web server. This is also something we're going to talk a lot about starting next week, is how that tunnel works in practice. Okay, but we'll call this, so it's called HTTPS. So you might not know what that means now, but when you're reviewing your notes for the final, you will know more than you want to know about it. And so this is how you communicate with it, okay? And so basically, if you can not get externally observed, and if you can not get internally observed, once you get it kind of in the browser in this SSL tunnel, then the security is pretty good, okay? Then it's going to go all the way to the server, okay? Now, the first thing the user is going to do is they're going to register. So the website's going to say, okay, what do you want as your username? What do you want as your password? And we'll ignore the username. Actually, let's not ignore it. So you put a username, password in, okay? And then it ends up at the server. Now, what does the server do with it? It has to remember it, right? Otherwise, there's no point, okay? So it has to store it somewhere, okay? So the server is going to have like a password table. It'd be like a database or something like that, okay? And it's basically going to be a list of usernames. And their passwords. Okay. Now, let's actually, we'll circle back to that. Okay, so this isn't a great solution, but anyways, this is one way of doing it. Then the user wants to log in. And so they say, okay, here's my username. Here's my password. And the server says, okay, great. I see that you're logging in. You're not registering. That means I should know who you are. So I'm going to take your username. I'm going to go searching through my database. I find your entry. So you're U3. I found you. And you just told me your password is dog, cat, mouse. And is that what I have written down here? If I have dog, cat, mouse written down, then I say, yes, that's you, and I log you in. Okay? And if I don't, if I have something else, I say, error, I can't find you. Okay? Or it depends. So there's actually been a push to give less information on those like error responses. So like previously it might say, oh, I have your username, but I don't have your password. Okay? But that's useful for an adversary. If I don't know your password, I know you at least have an account, right? And so for the right kind of websites, just knowing that someone has an account based on their email address, that could be private information, right? Even if I can't get into their account. So now it's sort of like, oh, there was an error. So either you aren't a user or you are the user and you entered the wrong password. So the website isn't usually very chatty about what went wrong, but something went wrong. Okay, now what happens if an attacker breaks in and they steal this password table? Okay, so they can log into everyone's account on this website, right? Plus, they could probably log into people's accounts on other websites because they tend to use the same passwords, okay? So now, for example, in Apple's keychain password manager, it warns you, it says, oh, I've seen this password in one of these leaks, right? So what happens is people break into these services. So they did it for LinkedIn, they did it for like RockU, which was like an early social network that we'll come back to in a second. And there's been a bunch of other like kind of highish profile examples, okay? And so they dump them on the net. Sometimes someone could break in and no one knows about it, okay? But anyways, eventually it becomes public information that this leaked. And then there's websites actually where you can type in your username and it will tell you, and you can, if you trust it, you can even put in your password and it will see whether it matches. And Apple uses this as well. So they'll look through these leaked kind of passwords. Okay, so let's say you're a web server. You want to do something about this. You're scared that your username password list is going to get dropped. Okay, is there anything you can do cryptographically to protect it? So I don't expect you to know the answer to this, but some of you might. Okay, so you may have heard of password hashes, okay? And so this is considered a better alternative than storing the passwords themselves. So what is a hash function? What do they do? So what you're going to store is exactly the same. You have U1, U2, U3. And in this case, instead of storing the password, you're going to store a hash of the password. And a hash function you'll learn about in 6.1.10. I'm not going to cover it. But basically, you can think of it as it's kind of like a mathematical function. It has one input and one output. So you pump any data through. The input can be any size. It doesn't matter here. The passwords are going to be smaller than the output of the hash anyway. And the most important property is that it's one way. So you can put an input in, get the output, but you can't start from the output and reverse out the input. And it's designed in a way to make it really hard to reverse. Theoretically, everything's reversible, okay? But the cryptographers, they say, well, let's make it so that it would take the lifetime of the universe to reverse it, kind of thing, okay? So you'll learn those like smaller details in a crypto course. But for now, just consider it like a truly one-way function. Now, the other thing that's important to note about it that seems like a nitpicking point, but is actually very important, is it's deterministic, which means if you give it the same input, you'll get the same output, okay? Not all functions are like that. Some functions in crypto are randomized. So like if you encrypt the message once today and you encrypt it tomorrow, the output's called the ciphertext and it will be different. You encrypt it 100 times, you'll get 100 different ciphertexts. They'll all decrypt to the same message, but they look different. Hash function's not like that. So when you encrypt it, when you hash it, same input gives you the same output. Okay, so basically what happens is the user comes along and they have their asserted password. So we don't know whether it's the right password or not. And their username. Let's say they're user 3, and they send their password in not hashed. Okay, so they send the raw password. Now it does go over the encrypted tunnel. Okay, so it's wrapped in encryption at the network level, but the hash that comes through is plain text. It's not a hash of the password. Okay, so they send the password itself. Then what the server does is it says, okay, you're U3. Okay, so I'm going to go down here. I find your entry. And what I'm going to do is I'm going to take your password star. I'm going to run it through the hash function. And then I'm going to check whether it equals the value I have stored here. Okay, are these things the same or not? Okay, so that's how it works. Now, is this better than not hashing? The answer is yes, because if the password dumps, it's one way. Okay, so I can't figure out what everyone's password is. I just have a hash of the password itself. Okay, the only problem with this is actually has to do with this deterministic feature, which is if I have a guess at what your password is, can I confirm whether that guess is right or wrong, even though the hash is a one-way function? I can, right? I can just guess, I can hash the guess and see whether it matches. If it matches, then I know, okay? And if I have 100 guesses, I could hash all 100 of them, right? And if I have 1,000 guesses, I could hash 1,000 guesses, right? And if the website uses the same hash function for all users, okay? And let's say the same hash function is used across lots of different websites, I don't even have to do it personally. It's just someone somewhere in the world had to do it once, right? So what people will do is they'll take a dictionary and they'll run it through a common hash function like SHA-3. And they'll say, here's every dictionary word's SHA-3. Then what I do is I get the dump and I just go and I reverse that lookup in that table and I say, oh, here's a hash that's someone's password. Is that a dictionary word? Then what they do is, because you can blow through a dictionary with a computer, you can hash at the millisecond level, right? So going through a dictionary, it's a big list of words, but it's not big for a computer. Then they'll try 2 dictionary words, 3 dictionary words. They'll say, well, sometimes people use the number 3 instead of the letter E, right? So they'll put a dictionary word, but they're going to spell it with like numbers. So I'm going to try all of those combinations and whatever. Or sometimes they'll get a raw password. Maybe it's like from 10 years ago. And they'll say, well, what were people using as their password? So we'll hash all of those, right? Or when we look at the passwords, we see that people tend to do this. Like they tend to do this like kind of pattern or whatever. And maybe we throw machine learning at this or something like that. Or like whatever your imagination is about what you can learn about how people choose passwords, that's the kind of thing that you would use to build a dictionary. Then you're going to hash every entry in your dictionary, and then you're just going to, put it on BitTorrent. And then everyone can just download it and reverse search it. Sorry, I got too excited. Okay, so this is better but not good. It's not the best, okay? What would be even better is if we could destroy this deterministic thing. Now, let's say it was a randomized algorithm. The problem is we would hash it once when we store it, and then we would hash it again when the user's coming along saying, this is my password. But if it's randomized, they're not going to match. So then we have no idea whether it's the right password or not. Okay? So we can't do a randomized algorithm. So we're kind of stuck. Deterministic means that you can do an exhaustive search. And I should note that just for terminology, people use the term rainbow table. So a rainbow table is just a hash of a dictionary or whatever. So when you download that, someone else went through they produced the SHA-3 hash of a whole bunch of common words or common passwords or potential passwords, and they give it to you as a file. That's called a rainbow table. So the one thing we can do is we can add what's called salt to the hash. And so salt is a random number. And we store the salt with the password itself. So if someone leaks the table, they're going to get the salt as well. So now the table will look like this. We have user 1. We have their salt. And then we have a hash of their password and their salt. And this means concatenation. And then for user 2, what we do is we choose a different salt value. And we hash P2 and S2. Okay, so why is this setting better? It's still deterministic. If I have a guess at what your password is, I grab the salt value. It's sitting right there beside your stored password anyway. And then I just add the salt value onto my guess. Okay? The only difference here is I have to build the rainbow table for you because you're the only user that has this salt value. Okay? So instead of having one rainbow table that can attack the entire list, I have to build a rainbow table for you, that one user with that salt value. And then if another user has a different salt value, I have to do a brand new rainbow table for each of them. So that makes the adversary's job a lot harder. You can't just go download a rainbow table because no one's done a rainbow table for that particular user that you're interested in. Okay. So what the salt does is it means you need a fresh rainbow table for every user. The other thing we can do is if we're trying to stop someone from trying, like building a rainbow table, so they're going to try 1,000 guesses, what we could do is we could slow down the process of computing the hash itself. If we make it slow, it's going to have a performance impact for the web server. Every time someone logs in, it's going to be a little bit slower, but that's okay because you're just logging in once a day. But for an adversary and they're trying millions of passwords every second, right? If slowing that down, that could make a huge difference for them. It could really slow them down, okay? So it sort of asymmetrically affects someone that's trying to guess passwords as fast as they can. It's a big speed bump for them, but for you, you barely feel it because you're only logging in once in a while, okay? So what people will do is, I'll just denote it this way, is they'll hash 1,000 times. So they'll just run it, they'll take the output and then run it through the hash again and again and again. They'll do 1,000 times. Instead of it taking a microsecond, it now takes a millisecond or something like that. And it doesn't really make much difference for the end user, but if you're an adversary and you're trying to compute as many passwords as possible, it makes a huge difference. So this is called the delay function, or and in crypto, we call it a PDKDF2, which is password-based key derivation function 2, because there's a second standard. Anyway, so it's a mouthful. I don't know if they cover it in 6110. When I teach it, I usually cover it, but they may or may not cover it. But anyways, that's the sort of concept. So this is sort of the state of the art for storing passwords, is you want a unique salt per user, so then the attacker has to build a rainbow table, and we want the hash to be a slow hash so that it takes them a long time to build the rainbow table. So if they go through all that work, yes, they could crack one user's password, but then it's just one user, and they're going to have to redo all that work to crack a second user. And so it really slows people down. Okay? And you can't truly, you can't protect it, because the problem is you have to do a comparison at some point, okay? And so if you lock it down so much that the adversary can't possibly decrypt it, then you're not going to be able to do that comparison either. It's going to be locked down. So that's the sort of intuition for why you can't push it further. So anyways. Okay, any questions about this stuff? Okay. Let me show you one other aside, and then we'll go back to our evaluation framework. So I talked about human-chosen passwords, and I mentioned that they're weak. So I want to illustrate this. So this is from a paper. So it's called, I forget what it's called. I'll link to it. I think it's already on the Moodle. So Joe Bonneau and others wrote this paper. Okay, so this is some weird looking graphic, and it probably doesn't make a lot of sense, but this is actually, I think, my favorite picture in all of computer science. I really like this. And so let me show you what it means. Okay, what this is it's a histogram or a heat map of a bunch of 4-digit pins that were leaked in a real attack. So there was a website, it was a social networking website a long time ago. I never used it, I never even heard of it. It's called RockU. It had some like music tie-in or something like that, sort of like MySpace before MySpace. And anyways, they had no good password policy, so you could type in any password you wanted. And so what the researchers did is they said, hey, a lot of people are just putting in 4-digit PINs, and that's the passwords that they're using. It's kind of crazy, but there's millions of users that have it. I wonder how random they are. Do people, when you choose a 4-digit PIN, are they choosing it randomly, or are they choosing it based on like a common 4-digit PIN or something like that? So they decided to analyze the data, and this is a visualization of the data. Okay, so the way that you read this chart is, let's say we want to look up a particular PIN. So I'm interested in, well, whatever. Just give me 4 digits. Shout out a number, someone. 8677. Okay, so the way I read this chart is I find the first 2 digits are on the x-axis, and the second 2 digits are on the y-axis. So 86 would be this sort of column here. And then we would go up to 77, which is right here. I might be off slightly, but let's draw the point here. It's really big. Okay, so let's we'll call this 8677. It's close. Okay, now you'll see that there's a color. Okay, so all of these, when you notice, you'll see like little squares. So each little square is a password. It's a unique 4-digit PIN. Okay, it's just kind of weird how you read the chart itself. And the how dark it is basically how common is that chosen. Okay, so in this case, it's kind of like a light blue, and so that means not a lot of people chose it. If it's really dark blue, that means a lot of people chose it. Okay, so the darker it is, and it's logarithmic, which means that the darker it is, it means like a really lot more people chose it. It's not like a linear thing, it like grows sort of exponentially, but those details don't matter so much. Okay, so this is basically, all of a bunch of pins that people chose. Now let's say they're machine chosen. So machine chosen pins, say the bank gives you a 4-digit pin, it's random. What would you expect to see from a color perspective? Okay, a uniform color. So it would be like a light blue and everything would be the same, right? Because every password is as equally likely to be chosen as every other password. Okay, so there shouldn't be some dark blue squares and light blue squares. Dark blue would mean that lots of people have that password. Okay, that would indicate that there's something wrong with the random number generator. Okay, does this look like a uniform light blue thing to you? It doesn't. Okay, so there's some weird lines and streaks and chunky things. Okay, and so that indicates that users aren't choosing their passwords randomly. Okay, so what do these things mean? What's a common 4-digit password that you think a lot of users would choose that has some human meaning to it? Okay, all right. So I heard. Okay, heard lots of things. Let's pick up 2 of them. So one of them was year and one was a birth date. Okay, so let's go look at this. Let's start with year. Okay, so a year can be any 4 digits. Like 6539 is a year, right? But probably would be kind of like years, like recent years. Okay, so I might look, for example, at like 19 blank blank or 2000 blank blank. Okay, so let's do 2000 blank blank. So like 2000, 2001, 2002. Okay, so the first 2 digits are going to be 20. Okay, and then the second 2 digits would be 2000, 01, 02, 03. So see this like dark blue horizontal line? That's basically the years from 2000 to about 2010. And this password thing leaked around 2010. Okay, so that's why it sort of dies out there. Okay, so this is very clearly, sorry, I'm just going to draw this up here. So this is like year, 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 year. And then if you want like 19, we would go over 1. So the first 2 digits would be 19. So this vertical line would be all the 19s. And you can see around 1930, it kind of gets darker. And then 1970, and then 1990, it gets really dark, 1980. And so that's exactly what that is. Okay, so this would be passwords like 19xx. Okay, now let's do birth dates. Okay, so what's a birth date? So my birthday is January 20th. So if I encoded that, now Americans do it differently than Canadians, right? So it could be 0120, or it could be 2001. So let's start with whatever. What do you want to start with? Month, month, day, day? Day, month. Okay, so day, day. Okay, so my birthday would be something like 2001. Okay, so let me do month, month, day, day, just because it is what I was thinking of. Okay, so month, month would go from 0 to 12. Okay, and so 0 to 12 are going to be the first 2 digits. And so see this, like, there's kind of like this weird, it looks almost like a castle moat here, okay? So what is that? So that's 01 goes to 31, and then 02 goes to 29, and then 03 goes to 31, 04 goes to 30 instead of 31, and then it goes back to, what is that? Okay, so that's the days in every month, right? Okay, so this is month, month, day, day. So you can see this exact structure here. And so if you were an alien and you didn't know anything about human civilization, and someone said, here's a bunch of 4-digit passwords that people, chose, you could back out the Georgian calendar from it. You would know, oh, it's important that, January has 31 days, but like February, and, it could have 29 or 28, depending if it's a leap year, so it's maybe a little darker there. And then for the Americans, you can see, oh, there's this like exact flip, right? We take this shape and we flip it down like this, and that's the reversal of month, month, date, date. Okay, what are some other things that people would choose? Either things that you would think that they would choose, or you can just look at it and say, like, for example, there's this diagonal line, right? Okay, so repeating numbers that have some sort of mathematical structure. Okay, so something like this, if you look closely, that happens at 44 and 44. So that's like 4, 4, 4, 4. You could find 5, 5, 5, 5, that type of thing. This one's popular. It's another repeating number, 69, 69. Don't know why that one's so popular. We could do 1, 2, 3, 4. So see that really dark square right here? That's surrounded by another bunch of numbers. So that's 1, 2, 34. Some of them are like musical references. Artist Usher, you might not remember him, but he had an album called 8710. It came out around the same time that this website was popular. It was a music website as well. So you can see it's a little darker there. This was a weird one, and let me see, 50. This reference was too old for even me. I think it's this one. Actually, that's not it. I found this and I looked it up, and I can't remember. I think I wrote it down. I either circled the wrong thing or I wrote down the acronym wrong. But it's one of these. I'm just going to circle one at random. I'll circle this one, 5691. And so I was looking at it a lot. This chart's interesting because any of those like dark squares, you can figure out what the number is, and then you can like Google it and be like, oh, why is that a number? Like 5691, that has nothing to do with it. And so this was even before my time, but back in the day, you had phones and they didn't have keyboards. They just had a number pad. And so if you wanted to type an SMS message, you could still do it, but you would have to, like, if you wanted to type in A, you would press 1. And if you want B, you would press 1, 1. And C would be 1, 2, 3. And then you would go to the next key. And so you could type messages out. And so anyways, if you type out the word love in SMS, it would be 5691 or whatever. And so people were choosing that as it. 4231 is also popular. That's here. Anyways, yeah, and then this whole diagonal is that there's some other like streaks that you could look into. These are all like 69 numbers all across there. This one is all 26. It looks like. I'm actually not sure why it's 26XX. I'm not sure why it's darker there, but that seems popular. Generally, people like smaller numbers, so smaller numbers are kind of in that lower left quadrant. So you can see it gets a lot lighter blue. Like there's a lot of regions here where it's like kind of lighter blue. And anyways, you could spend a long time looking at this chart. I encourage you to do it. But the moral of the story is that human chosen passwords are bad. From a guessability perspective. And if I were to guess your 4-digit password, there's no way I'm going 000, 001, 00. I'm going to go 19, I'm going to go 2020, 2019, January 1st, January 2nd, I'm going to try 6969. I'm going to try 1, 2, 3, 4. Okay. So that's how, now with a 4-digit, I can exhaust the whole space. That's not a problem. But with like letter, alphanumeric passwords, that's how people attack them. Okay. So when they build rainbow tables, it's not of like every character combination. It's of past leaked passwords. Every dictionary word that I can find. Every word, if I just search the internet and I pull down a random HTML file and I look where the spaces are, and I consider all the combinations of letters between two spaces, I'll call that a word, and I'm going to add that to my dictionary or whatever, okay? So if your password is anything that you could Google and find, like on another website, like a reference to anything, like chances are it's in a dictionary. Or if it's like some weird permutation, like where you substitute numbers for letters or things like that. Okay. All right, so let's go back. So that was meant to just sort of help with this resilient to guessing type of thing. So user-chosen passwords, very bad. Machine-chosen passwords are better. Online, offline. Offline is when you have that hash password file. So you have someone leak the hash word password file and you're hitting it as fast as you can. And then online would be like you have to go through a website. Okay. Shoulder surfing we can consider. So I just penciled these in during the break. So we call it resilient to observation. And so basically, if you have to type or draw your password, then it's not going to be resilient to shoulder surfing. If you don't have to type it because it's like a key or something that's automatically transmitted, then that's good. And let's just skip the middle category. Physical theft is another one. So like basically, is it if I steal the right thing, can I log in as you? So we don't want that. So we want it resilient. Okay. So if there's nothing to steal that would let me log in as you, I'll put here nothing to steal. That's basically sufficient for a login. And then here it would be there is something I could steal. And if I steal it, then I can log in as you. And then for deployability, we could think about cost. The best case is you don't have to buy anything new, so no new costs. So if it's just changing code or something, there's always a cost to everything, but we'll just consider that. What I'm thinking is like an RSA token. So like if you have 1,000 users, you have to buy 1,000 RSA tokens. So that's something that's not negligible in terms of costs. So there would be a cost per user. And then it might be like a fingerprint reader for a building, and you have to buy it once, but it doesn't matter if 100 users walk by or 10,000 users walk by. It's the same cost, right? So you did have to buy something new, but it wasn't on a per user basis. So it's a cost, a one-time cost, let's call it.
So it's half.
And yeah, we'll give that a half, yeah. Okay, so then what we can do is we can work on our table. And so let's pencil some of this table in. We maybe don't have to do the whole thing. So yeah, ideally what you would do is when you do the table, because these are just class notes, I gave each label a short form like U1, U2. But normally in the table, you would actually write out the full column, so you don't have to do what I'm doing, which is bouncing back and forth. I apologize. When I screen record, the scrolling goes crazy. So if I can find the right screen. Let me try and do it more manually. Okay, let's just keep it here. So I have the notes here anyways. Okay, so U1, let's do that one. So U1 we said was physically effortless. Okay, so do you have to type or draw something every single time you log in? Do you just have to do it once, or do you not have to do it at all? Okay, so for a password, if you're just using plain old passwords, you have to do it every single time. Okay, so we're going to say it gets no dot for passwords. For biometrics, you don't have to type or draw. You do have to do some physical action. Maybe, I don't know. So this is, we should actually go back to the definition. So like, would a scan of a fingerprint, are we going to count that or not? So like, in my mind, like typing something out, it requires me to memorize it, remember it, and then type it out, and it's 20 characters. I might make mistakes typing it out. So that's why I don't like it. If I put my fingerprint, yeah, I do have to do that physical action, but it was kind of like a brain dead, like I didn't have to think about it or anything like that. So anyways, I should define these dots a little bit better to take account, but I'm going to give biometrics a full dot for that reason. But once again, yeah, it's all about your definitions themselves. Okay, tokens. So this is like tokens are RSA tokens. In this case, I have to type it in every single time, plus I have to type this extra digit. It's even worse. So that's getting no dot. Two-factor authentication, same thing. I have to, this is SMS-based two-factor. Let me call it SMS. And tokens, I'll call it RSA just to, I copied this table from the notes last year. We used slightly different notation. Okay, SMS, same thing. I have to type it in. Password manager, I just have to type it in once. Then I unlock my manager, and then it's going to type it in for me. I don't have to type it in, okay? So we'll give that a half dot. A certificate, my computer will just send it. I don't have to do anything. Sometimes you want to wrap it in a master password, so that depends. Let's assume that you don't do it, so then we'll give that a full dot. Single sign-in, I have to at least sign into like Facebook, but then once I'm signed into Facebook, I don't have to sign into subsequent websites, so that's a half dot. Graphical passwords, I have to type it, I have to draw it every single time. Okay, so that it gets no dot in that case. Okay, how much do I have to memorize? One password, 0 passwords, 1 password, or 100 passwords. So for passwords, I have to memorize 100 of them. That's the worst, so it's going to get no dots. Biometrics, I don't have to memorize anything, so that's good. I'll get a full dot. RSA, I still have the password. So I have the second factor, but I still have a password as well. And if I have 100 RSA accounts, then I should have 100 passwords that are all different. So that gets no dot. Same with two-factor authentication. You still have a unique password per site. A password manager, I just have one password. So I'm going to give it a half dot. Certificates, I don't have any passwords. It's great. Single sign-on, same, just have one password. And then graphical, I have lots of passwords. Okay. Now, you notice something curious. These columns are actually exactly the same. Okay. So in that case, you might go back and say, am I actually asking a different question, or am I asking the same question in a different way? Like if I'm measuring how many times I have to type in a password and how many passwords I have to know, they're kind of like, it's kind of like two columns that are capturing the same identity or the same idea. And then you might think, well, maybe there's something here that would separate them. Like maybe there's some other alternative where you have to know extra passwords, but you don't have to type them in or something like that. And so in this case, I think it was just a mistake. I think we just happened to come up with two columns that had the exact same evaluation. And so if I was doing a second pass over this, I might collapse those two into the same column, or I might go back and tweak the definitions a bit so that they're truly measuring different things. So this is the kind of mistake that you might see when you try and do it yourself. So if you have a completely empty column, a completely full column, two columns that are the same, anyway, those are times to reevaluate or ask yourself again about the columns. But anyways, let's just press on. So U3 is nothing to carry. So passwords, I don't have to carry anything. They're in my brain. My brain's going everywhere with me. Biometrics, I don't have to carry anything. They're in my face, finger, iris, whatever. RSA, I do have to carry something. It's something new that I wasn't carrying before, so that's the worst. I'm not going to give it a dot. SMS, I have to carry my phone. If I don't have my phone, I can't log in, but I'm carrying my phone anyways. So that's sort of halfway. It's not like the RSA token where I have to remember to carry it. So we'll give that a half dot. Password manager, it's in my head or it's stored on my computer. Certificates stored on my computer. I have to take my computer, but presumably I'm logging in from my computer anyway. So it's not even like the phone where I'm carrying it anyway. It's like, it's the thing I'm logging in from is the same thing that's storing it. So let's just consider that as I don't have to carry anything new. Sorry, I put that in the wrong spot. Oh yeah, and I'm being lazy with the dot. So it gets a full dot if you don't have to remember anything, because that's what we want. Or to carry anything, sorry. Single sign-on, I also don't have to carry anything new. And graphical passwords, I don't. It's all in my head.
For the assignment, we should write every sentences when you are filling the table.
Okay, yeah. So for the assignment, this is what I want. I want a clear definition of every column. I want to know what's a full dot, what's a half dot, what's a part dot, or no dot for every column. Then what I want, and the assignment will be broken down. It'll be like, okay, write your columns, write this. Like, you're not going to miss stuff. It's going to be in the assignment itself. But yeah, when you do the evaluation, I also want a sentence that says, I gave a half dot to SMS on U3 because a half dot means this, and SMS meets that half dot because of this, or whatever. Yeah. So a proper evaluation framework, you would have a sentence somewhere in the write-up for every single dot. So if I'm reading it and I'm like, you know what, password managers on U3, I think that's a half dot instead of a full dot. Why did the authors think it was a full dot? I might not agree with them. I might disagree. That's fine. But it should at least be in the paper. I should at least be able to find the sentence that says why, and I can understand their rationale why. Yeah, and it's reasonable. But like I say, different people will evaluate things differently, or the dots will mean different things. And so not everyone has to agree with your table, but you at least have to justify why you did it. Okay. S1 is resilient to guessing. So we have online and offline guessing. So this is S1 and S2. Okay. So passwords, basically, you can guess them. Even an online attack, a password isn't necessarily high entropy enough. So we'll give it no dot. Biometrics are in the middle, so they have enough entropy for an online attack, but an offline attack, if you have a hash of the fingerprint, you could brute force it. RSA, they're going to give you a long digit. I'm going to say that long digit is enough for an offline attack. And same with SMS. I might be deviating slightly from our definitions, but I'll say it this way. Password manager is complicated because the master password is still a human chosen password. The passwords it's giving to me are great, right? They're long, like the Apple passwords are like something like 20 alphanumerical character, like base 64, like capital letters, small letters, numbers, some special symbols, and they usually are in like clusters of 5, and there's 3 5, so it'd be like 15-ish alphanumeric. So that's not quite a key strength, but it's pretty strong. But the problem is the master password. I have to choose it. You know my master password, then you get all my passwords. It doesn't matter how strong they are. So I'm not going to give it anything because of the master password. So it's kind of brutal, but yeah. Certificates, I might give it both. Single sign-on, same thing. You have a password, master password. And graphical passwords don't get anything. Okay, biometrics, or sorry, S3 is resilient to shoulder surfing. So I can shoulder surf your password, so no dot. Can I shoulder surf your biometric? Kind of, it depends how you define it. What do you think? I'd say you can't, I guess. Why not? You should probably, it comes down to how you define it, right? So like if I take a picture of your face or a video of your face, I could maybe replay it or things like that. But there isn't anything to actually shoulder surf. It's not like I can see the like digits coming off of your fingerprint and going through. So it's close. RSA token, I can look over your shoulder. SMS two-factor, I can look over your shoulder. Password manager, I can if it's the master password, but if it's not the master password, then I can't. Like it automatically puts it in. So I don't know, I can't remember if we did a half dot, but since I'm just making this up kind of as we go, let's give it a half dot just for the idea that once your master password's in, then if you go to Facebook, it just populates it and there's nothing to see in terms of typing it in. Certificates, there's nothing to see. It just happens automatically. Single sign-on, it's kind of like the password manager. I could surf your master password, but once you're signed in, then I go to the new app, I just say connect with Facebook, and then boom, 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 and then I'm in, and I didn't have to type any passwords or anything in. Graphical, I have to type it in every time. S4 is resilient to physical theft. So is there anything to steal? So passwords, there's nothing to steal, so that's fine. Biometrics, we can go back and forth on. I would say that I can lift your fingerprint, right? I can build a rubber finger. I can 3D print it with your fingerprint. This has all been done before. I can log in as you. Your face is maybe a little harder to steal, but I could maybe get like some sort of, like maybe it wouldn't be a physical thing. It would be like a video or something that I would play into the camera. So anyways, so let's say not, you might give it a half dot. It depends on how you define it. RSA, you think, okay, I can steal your RSA token, but can I log in if I have your RSA token? No, I still need your password, right? So even though I can steal one of your factors, it's still as strong as a password, right? Because you still fall back. All stealing does is it turns this dot into this dot, and this dot was already a full dot, right? Okay, and similar with SMS. If I steal your phone, that's fine, but I still need to know your password, okay? So if I can't steal your password, it's in your brain. And so these two things don't decrease the security. Password manager, same idea. Certificates I can steal. So it's usually stored on your computer. The way we've been evaluating it is as if you don't have to type in a master password. That's why it was doing so good on usability, because it just sends it, and scalability and things like that. But if I get your computer, it's in a file on your computer. Now I have your certificate. So I just have to steal your computer. So it's bad on that regard. Single sign-ons like a password manager. And graphical passwords, same. There's nothing to steal. It's stored in your head. Okay, and then deployability was how much does it cost? So passwords don't cost anything. That's why they're popular. Biometrics do cost something. The cost would depend, but let's say it's a fingerprint reader on a phone, or you want to do fingerprint authentication on a phone. Every phone needs a fingerprint reader, okay? So that's a cost per user. So if there's 1,000 users, you have 1,000 phones with 1,000 fingerprint readers. So we'll give it no dot, meaning that it's a marginal cost. For an RSA token, you have to give a token to every user. You have 1,000 users, that's 1,000 tokens. So similarly, no dot. SMS, you have to give everyone a phone. Now, maybe they already have a phone, so you can argue about that. So if you want to consider the fact that everyone already has a phone, then it's a full dot. If you want to think about everyone having to go and get a phone, then it's a no dot. And so it depends. Let's say that everyone has a phone already. So like it didn't cost Concordia anything. They didn't have to go buy a whole bunch of new phones for everyone. Password manager, there's nothing to buy. Certificates, there's nothing to buy. Single sign-on, there's nothing to buy. You do have to put up a server that will like accept these requests. So that's kind of like a one-time cost. Like Facebook puts it up, but then it doesn't matter how many, once it's up, it doesn't matter how many users log in or don't log in. So there is a new party, new server, so we might give that like kind of a half dot. And then graphical passwords, there's no extra cost. Okay, so anyways, you get the idea, hopefully, of the table. So this is how you go through it. The last thing I'll show you quickly is what does this look like in a professional kind of setting? So there's a paper that's also linked to from the Moodle, and they did this exercise, and they wrote an entire paper about it. Let me see if I can zoom in. Okay, and so you can see that the number of rows is a lot more than we considered, but this kinds of things that we considered are there. They also consider different brands of the same kind of idea. So password managers, basically the difference between these two is whether there was a master password or not. So that changed the evaluation. Proxy we didn't cover. Federated is that single sign-on. So there were a couple different ways of doing it. This paper is a little bit older, so they evaluate slightly differently. They had 2 different graphical passwords. There was these cognitive passwords that we also didn't talk about, where they kind of give you a puzzle that you have to solve mentally. There was a bunch of paper-based things. So you had these like pieces of paper that had a bunch of codes, and you would like based on where you're logging in, you would like circle different letters and type them in. So we didn't talk about those. Hardware tokens, so we talked about RSA. There's also some other ones that have slightly different properties. Phone-based, so this is 2-factor authentication. Biometrics, and then they also looked at recovery as well. And so we set that to the side, but in the paper they looked at recovery. And then you can see that, so this was the paper that came up with the evaluation. It was probably the first paper to do like this kind of evaluation framework. And then lots of paper have been written since that repeat this. And you can see, so they have usability, deployability, security. I tried to match our columns to columns that are in the paper itself, but sometimes I simplified the words or things like that. But anyways, you have to kind of turn your head sideways, but you can see they have lots of usability ones. So memory-wise, effortless is basically like, do you have to memorize things? Scalable for users is kind of like, how much work is it to sign up for 1,000 accounts versus 1 account? Nothing to carry, we saw. Physically effortless, we kind of considered. Easy to learn was something someone suggested, so that's sort of understandability. How efficient is it to use? Errors is an important thing. Are you going to make mistakes typing it in? And can you recover from loss? Deployability, anyways, you can read them yourself. I have to read the whole table out. But this is what it would look like if you wanted a paper in the area. This was at a tier 1 conference, like one of the big 4 conferences. So this is a very good paper, an excellent paper. And so what does it mean for you? So what it means for you for your assignment is, I don't need this level of detail. Okay, even for a project, I mean, this would be an A+ project. But even for a project, it doesn't have to be like quite at this level, but it has to be better than what we did in class. Okay, so I want something that's better than what we did in class, but maybe not as good as this. The other thing about this is I don't have the paper itself at my fingertips, but if you look at the paper, it's like 40 pages long, and what they they define every column, right? So you can go look up what does it mean to be browser compatible, and they'll have an exact definition. What's a full circle? What's a half circle? And then somewhere in the paper for every single dot, there'll be a sentence that says, you know, we gave browser ID a half dot on browser compatible because of this reason. There'll be a sentence somewhere that says that. And so that's why the paper, I mean, you can see all the different combinations and things like that. So it turns into a 20, 40 page paper as a result. Okay, so that's evaluation frameworks. Any questions about them? Okay, so think about them for a week. Next week, ask me some other questions, and you're going to have to do one of these. So make sure that you're clear on it by next week. Okay, thanks. I'll see you all next week.